Gas chromatography, or GC, is a widely used for analytical technique for separating and identifying organic compound. In this technique, the sample is vaporized and carried through a column by an inert carrier gas such as helium or nitrogen. So separation occurs based on the interactions of the compound with the stationary phase inside the column. Gas chromatography is commonly used in organic analysis because it is efficient, accurate, and reliable.
Next, we will look at the objectives of this experiment. The first one was to determine the retention time of N-butanol and 2-propanol. The second one is to identify the components present in a standard mixture based on their retention time. The third one is to identify the component present in an unknown sample. Last but not least, to determine the effect of temperature on the retention time and resolution of the components.
Let's move to the instruments of gas chromatography. The main component of a gas chromatography instrument include the carrier gas, injector, column, oven, detector, and data analysis. So let's go through to each of the part. The carrier gas is an inert gas such as helium or nitrogen. It functions as the mobile phase that carries the vaporized sample through the column. The ejector part is where the liquid sample is introduced into the system. It is heated to ensure the sample is rapidly vaporized. Next, the column, which is located inside the oven, contains the stationary phase. This is where separations of compound occurs based on their boiling point and interaction with the stationary phase. The oven controls the temperatures of the column, adjusting the temperatures effect, the retention times, and separation efficiency. Next, the detector detects the separate compounds as they exit the column and convert them into electrical signals. Finally, the data system records and displays the signals as a chromatogram.
Now we will look at the procedure. The first one is sample handling. The sample was first prepared by rinsing the syringe and drawing a volume slightly more than required. The syringe was checked for air bubbles, which were removed by gently tapping, and the plunger was pushed to the required volume at eye level. Any excess sample on the needle was wiped off with a tissue. Next is the experimenter. The GC instrument was switched on and allowed to complete its setup. The GC was set with an initial and final oven temperature of 70 Celsius, an injection temperature of 180 Celsius, and a detector temperature of 180 Celsius. Each component sample was injected individually to determine its retention time, followed by the injection of a standard mixture to identify components by comparing retention time. The unknown sample was then injected and the component presents were identified. Next, the column temperature was later changed to 100 Celsius to observe the effect of lower temperature on retention time and resolution, and the oven temperature was set to 140 Celsius to examine the effect of higher temperature. For instrument operation, the injection type was set to manual, and the injection location was selected as spec. High concentration samples were run in split mode, while low concentration samples were run in spitless mode. Column number 2 was selected with the inlet set to the back, the mode set to constant pressure, and the outlet set to ambient. The detector was set to FID, and the injection parameters were 1 microliter volume and 5-minute injection time. The method was safe, operator and sample information were entered, and the run method was started. Samples were injected quickly and data were analyzed by loading the signal and creating a calibration table. The same steps were repeated for all subsequent samples.
So, as you can see in this result, all of these compounds that were analyzed have shown the chromatograms where the longer retention time for N-butanol than 2-propanol. So, why this happens? This is because of the boiling point that affects the retention time. 2-propanol has a lower boiling point which is 82 degrees Celsius, so it evaporated faster. In contrast, N-butanol has a higher boiling point of 180 degrees Celsius, causing it to elute more slowly due to stronger interaction with the stationary phase. Next, the unknown compound were identified by comparing the chromatogram with the standard chromatograms, which is the unknown sample showed a peak with a rotation time matching that with N-butanol. Therefore, it confirmed that the unknown compound was N-butanol. Furthermore, we analyzed the effect of column temperature on rotation time. As the column temperature increases, the rotation time decreases because higher temperature allows the compounds to adhere faster. So, in terms of peak resolution, increasing temperature may result in sharper peaks. However, excessively high temperature can reduce resolution and cause peak overlap. In this experiment, no peak overlapping was observed, indicating that the temperature used was to be in the optimal range.
In conclusion, gas chromatography was successfully used to determine the rotation times of 2-propanol and N-butanol and to identify components in both the standard mixtures and the unknown samples. Increasing the column temperature was found to reduce rotation times and affect the resolutions. Overall, the objectives of compound identifications and studying the effect of temperatures on chromatographic separations were successfully achieved.